Okay, so we are continuing with our look at SIR models. We are just introducing this guy. This is a model that tries to look at how an outbreak of a disease propagates. So we are looking at disease transmission. We've already established what S stands for, what I stands for, and what R stands for. And we are going to say these are classes of or groups of people at any particular point in time t. So in other words, we have got a group at a certain time t of susceptibles and a group of infected people at a time t and a group of recovered people at a time t. But of interest to us now, we want to look at the underlying assumptions of this model because we established that, of course, we are going to have some movements of people that are susceptible, that become infected, and then they recover. But is this as straightforward as it looks? Because we have got issues such as migration. Like I said in the previous video, one of the reasons why COVID-19 managed to get into Europe is because of migration. People were moving on for business reasons. People were moving because they went there to see their families in China or their families in America or somewhere in Europe. So what we then have is we assume that maybe migration is not taking place. We assume that people are not being born. What are the underlying assumptions of a basic SIR model? So those are the ones that we want to discuss according to the paper by Howard that we are looking at. So the disease transmission itself is derived assuming several strong assumptions, very strong assumptions. By strong, we are actually emphasizing on them being realistic, like we are talking about a population that consists only of humans. All right, so we are talking about being at a school, maybe at a hospital, or in town, in a city, or animals, maybe. So we are talking about these living things that we can actually talk about. All right. Then we partition the population into three groups or compartments, which is something I mentioned earlier on. We've got susceptible individuals, we've got infected individuals, and we've got recovered or removed individuals. So removed is better because it talks about the dead or those people that are no longer sick of the disease, but they don't go back again to being susceptible. So we are going to denote the sizes. So we are saying how many people are in each compartment. So we've got ST people in the susceptible, we've got IT people in the susceptible, in the infected, and RT people in the recovered. And as we have said, there are many assumptions behind the model. And one of them is like, some of them rather, large closed population. So it means that we don't add to the population. Remember I talked about migration? So migration is not under consideration. But then it doesn't make sense, isn't it, in the case of COVID-19? So we are simply saying that there is no migration, there is no new birth, there is no natural birth, and natural death does not exist. So nobody dies naturally. People simply die because of the disease. And the infection here has got zero latent period. And when we're talking about a latent period, so we simply say that, look, I have the disease, right? And you get into contact with me, and immediately you also contract the disease. There is no time for you to go home and then start feeling hot, high temperature. No, there is no time for that. The moment when you get into contact, then you also have the disease. So there is no latent period. So an individual becomes infectious as soon as they become infected. So a person now is able to pass the disease to someone else without waiting for those things that I was talking about, like temperature getting high or something like that. Then recovering from infection confers a lifetime immunity. So once you contract COVID-19, you get hospitalized, you recover, you will never contract COVID-19 again, according to this assumption. That's why we said there are some strong assumptions. Then there is this thing called mass action. So mass action simply means that this is the mass action mixing of individuals. And when we talk about mass action, we are referring to the fact that, look, as people interact, because there are the susceptible people and then the infected people. These two groups of people are going to interact, and the rate at which the susceptible individuals become infected is directly proportional to both the population of the susceptible individuals and the population of the infectious individuals, and inversely proportional to the total population size. All right? What are we saying here? We are saying, look, as we have more people that are infectious and as they interact with more people that are susceptible, then the disease also has to spread much quicker. That is the sort of thing that we're talking about here. And there is a mathematical expression for that, but we'll discuss that as we go. So that is the essence of mass action, and it's an assumption that the rate of encounter between susceptible and infected individuals is proportional to the product of the population sizes. So mostly in modeling, when we talk about product, we are saying we're multiplying, right? We are multiplying the susceptible times the infected, and this is an interaction. They are meeting. That's what we are talking about. We are saying now, at this point, the susceptible are actually meeting the infected. All right. So doubling the size of either population results in twice as many new infections per unit time. So we are simply saying that if we've got 5 people with COVID and 5 people who are susceptible, so once we double and say now we've got 10 people that are susceptible, that's what we're talking about. When you say we double the size of either population, then we get double the number of new infections per unit time. And this requires that the members of both populations are homogeneously distributed in space and do not mix, mostly in any smaller subgroups. So obviously now, as we operate, as we move on with our lives, every person will encounter every other person per unit time with equal probability. So we are going to say, look, there is a probability of interaction. So we are going to enforce a probability in the mass action. So the transmission rate is going to be represented by something that represents the average number of contacts per person per time multiplied by the probability of disease transmission in a contact between a susceptible and an infectious individual. So we are going to include the probability of transmission, because when people meet, it doesn't necessarily mean that if you are wearing, you put on your mask and then you meet with someone, then you practice safe distance between you and the infected person or the other person not infected necessarily, then the probability of contracting COVID-19 becomes low. So we have to consider such cases as well. And at the end of the day, it becomes a constant probability that we apply across the board. All right. So these are the assumptions. And in summary, we are simply saying the population is going to be well mixed, that every individual has got an equal chance of meeting another individual in that population. So any infected individual has an equal chance of meeting any susceptible individual. And we're talking about a constant population size. The number of people in S plus the number of people in I plus the number of people in R, the total is going to give us N, the total population, and it remains constant. There are no births, there are no deaths that are natural. So demographic stability. Then we also assume constant transmission and recovery rates to mean that the transmission rate, the rate at which the virus is or the disease is transmitted from one person to another, it is constant, and recovery also is constant. The rate of recovery, it is also assumed to be constant over the course of the epidemic. Well, this is not really true, because sometimes there are interventions by, public health interventions, behavioral changes, development of immunity. But then we assume that even though that can be true, but there is constant transmission and recovery rates. Everybody is equally likely to get the disease. So homogeneous susceptibility. So we assume that all susceptible individuals, no matter where you stay in a crowded area, you stay in an open space area, the probability of you contracting the disease is the same. It doesn't change. And also, once you recover from the disease, you are guaranteed lifetime immunity. So you are not going to go back again to being susceptible. All right.